So before I dig in further, let me start with a brief overview of New York Power Authority, which was initially established in 1931, and it is one of the largest state public utility in the United States. So in this expansion, there are two main key initiatives that we are trying to focus on. One of them is the creation of the digital twin of the New York State grid. And in this case, what we are focusing on is encompassing a complete mathematically accurate and AI-based model of transmission distribution systems, communication network, energy market emulations, as well as forecasted sources for weather and load that will help us to predict the accurate power output from renewables. And some of the use cases that we have come up with to think as the potential applications are realistic testing of technologies, control room advisory, which basically means to make this digital twin at the grid scale so mature enough that it can be now used in a control room environment.
If you read the Grid Modernization Index Insights report that we did a few years ago, we looked at some of the key driving forces within the utilities sector that help to foster innovation and scaling technology across scaling technology deployment. And one of the things in that report was the changing nature of utilities' relationship to innovative startup companies. And some of our utilities have innovation labs. They're actually reaching out and looking for startup companies where they used to have relationships only with companies that were capitalized in the $10 million or more. Now some of them are developing relationships with really early stage companies. And so we thought it would be really interesting to hear from one of our utilities that's in that space of really trying to leverage innovation. And so we asked Rahul Kadavil to come from the New York Power Authority to talk, not just right here on stage, but he's got a table out in the main area out there where they've got some kind of technology showcase for you that you can visit. So I'm going to ask him to come forward. You can just use the mic. If you want to just use the mic, you don't have to get all dressed up. And thank you. We're going to give a TED Talk, a NYPA TED Talk.
Oh, wow. Oh, is my slides going to be put in over there? Okay. Sorry, wrong presentation. Yeah. Any help? Oh, great. Okay. All right. Oh, does everyone hear me well? Am I clearly audible? Okay, great. So, greetings everyone. My name is Rahul Kadavil. I'm a manager at Advanced Grid Innovation Lab for Energy, which is a digital service offered by New York Power Authority. And in this presentation, what I'm going to cover is who we are, what we do at NYPA, as well as how we are accelerating the adoption of new technologies at scale through the use of this agile facility. Okay, it's stuck. Any help? Yeah. Interruptions happen. Yeah, exactly. Okay. Oh, great. Okay. Nope. Doesn't like me. Okay. So before I dig in further, let me start with a brief overview of New York Power Authority, which was initially established in 1931, and it is one of the largest state public utility in the United States. We own and operate transmission and generation assets. We don't own or operate any distribution networks. So in terms of generation, we have around 17 generation facilities that are spread in throughout New York State, out of which 80% of the fuel source comes as hydros, and the rest, 20% comes from natural gas plants. In terms of transmission, we own and operate about 1,550 circuit miles of transmission network within the New York State, out of which about roughly 15% of the lines are at the 115 kV level, and about 34% of the lines are up to 30 kV and above. So it's essentially, in totality, we operate about 115 all the way to 765 kV worth of transmission network, and we share a portion of that bulk transmission system with the rest of the transmission owners within New York State. So in the timeline that I'm showing on the right, pretty much highlights the key motivations behind establishing Agile. So New York State has set up ambitious goals to tightly integrate clean, renewable energy resources as a part of its Climate Leadership and Community Protection Act. So they have set up quite a bit of a milestones to achieve when you look at these timelines. So what they are saying is in 2025, we need to get 6 gigawatts of generation from solar. By 2030, 70% of our generation should be from renewables. By 2035, we are expecting about 9 gigawatts of energy being dumped by offshore wind. And by 2040, we are expecting it to be a completely zero-emission carbon-free grid. Now, to get to each of these milestones, there are significant challenges. Most of you might be aware that when it comes to renewables, these sources are intermittent, especially your wind and solar. And the traditional setup of our electric infrastructure has been unidirectional. That is, they have been set up from the generation centers to serve the loads. But in the presence of renewables or distributed energy resources such as DERs, there will be a bidirectional flow back into the grid, which was not the way this entire grid has been designed since the past or since its inception. The other issue is all our existing protection schemes needs to be re-evaluated in the presence of renewables. So anticipating all these issues, we know that the future grid will be completely complex and too stressful when it comes to managing and planning them in the presence of renewables so that they operate in an optimal capacity. Now, to address those challenges, most of the solutions can come as new or off-the-shelf technologies as outcomes from applied research and development. However, to test these technologies directly into the field can introduce a negative interaction that may be harmful for the operation of a live power system. And that's where NYPA created Agile to bridge the gap between this R&D effort and the field deployment. So what we are trying to say is all these smart technologies we can test inside Agile before they can be actively deployed in the field. And the way to do it is we actively maintain a power system representation that runs in real time through the capability of using real-time simulators. Now, what do I mean by real-time simulators? They are computationally expensive asset which can recreate exactly 1 second of a simulation time as it occurs in the real world for 1 second. And that helps us to interface simulated power system models with actual devices, so that way they will react as if they were actually set up in the field. So all this is to essentially say that Agile is set up to de-risk these new technologies before their field deployment. So this slide represents the complete technology stack that we have in Agile. If you look at the bottom row, we have actual hardware devices such as protection devices, intelligent electronic devices, which are your substation automation controllers, GPS clock, substation mock-up, coupled with simulators from RTDS and OpenRT that can actually simulate not only power system, but also run communication network emulations. One level above is all the offline as well as the real-time simulation software stack that we have to prepare all of this model stack and resources. Now, we have invested significant time and resources to create a fully validated, a full electromagnetic transient model of the complete New York State grid. And we have several flavors of it that runs in a bunch of platforms, as are visible here, HyperSim, ePhaserSim, and RTDS. So all this is to say that this allows Agile to offer its stakeholders to run the following outcomes that have listed at the top, that is grid modeling, simulation, real-time hardware and software in the loop, communication network emulation, economic analysis, application development, and hardware testing. So essentially, we have the capability to recreate a phenomena that occurs in the microsecond time range, such as lightning strikes or switching surges, all the way to slow evolving events such as generation dispatch that occurs in minutes and hours. So this is just a physical layout of the lab. So initially, we started with a small footprint of simulators back in our White Plains office in 2017. From there, we expanded into a 10,000 square feet facility that houses all our simulators that you can see in the bottom center figure, workstations, warehouses, and servers, and even actual substation equipments, which is now located in the College of Nanoscience Engineering at Albany. We had a grand opening of this lab in May of this year. So one of the interesting things that we have added in this new facility, if you can focus on the image in the bottom right, is a visualization room where we can showcase all the results from our simulation. If you notice, all the lights in the ceiling of that room, we have directly hooked it up with our real-time simulators. So when we create any kind of a disturbance in this simulated grid, they are directly controlled onto the lights, so that gives you a feeling of immersion as to how a fault occurs and what is that experience that it feels like. We are taking this visualization approach one step further by introducing a virtual reality cave, wherein it will allow an end user to literally walk into a grid simulation and experience it from higher dimensions. So in this expansion, there are two main key initiatives that we are trying to focus on. One of them is the creation of the digital twin of the New York State grid. And in this case, what we are focusing on is encompassing a complete mathematically accurate and AI-based model of transmission distribution systems, communication network, energy market emulations, as well as forecasted sources for weather and load that will help us to predict the accurate power output from renewables. And some of the use cases that we have come up with to think as the potential applications are realistic testing of technologies, control room advisory, which basically means to make this digital twin at the grid scale so mature enough that it can be now used in a control room environment. Predictive operations means representing future states of the power system to test for different scenarios. One of them being, what would be the impact if there is an extreme weather event at a certain location in the grid? Education and training, root cause analysis, which basically is historically replaying the events so that you can examine what went wrong in those kind of scenarios, for example, a blackout. So here is an overview of the conceptual diagram that shows all the individual components that we envision towards developing this massive grid-scale digital twin of the New York State grid. So essentially, the core of this digital twin is just a set of electromagnetic domain and phasor-based models that can run in real time as well as offline. So real time, again here, refers to the power system representation that runs with hard real-time constraints. And that is the source that enables us to interface actual physical equipments, such as substation protection relays or any other controllers, so that we can characterize them instead of using a software model which might be less accurate compared to the actual physical hardware, as to how they will behave or respond when you subject them to disturbances or any other anomalies of interest. So this is the next big initiative. So all this time, what I've been talking about is testing of low voltage applications, such as protection relays, grid controllers, or control systems of power converters. But what if you want to test your actual inverter-based resources, such as a PV array, a wind turbine, batteries, or even electric vehicles? And that's where we come up with this power hardware in the loop test bed, which is nothing but a big amplifier that can set as an intermediary between our simulators. So it can take those low voltage signals and boost it up into thousands of volts. That way it can directly talk to these high power devices, such as batteries, wind turbines, and what have you. So essentially what we are saying is all the power system models of the New York State grid can still be simulated within our simulators, but at those locations in the grid where you expect an actual wind turbine or a PV resource, it will be replaced with an actual device instead of a simulated model. So now you can actually have a performance and characterization in a closed loop simulation and see how well they respond in the presence of any disturbances. So who are our stakeholders? We primarily work with other internal NIPA departments, utilities, national labs, and even startups, where they take the funding from either from us or NYSERDA or US Department of Energy, and they use our facility as a testing environment to de-risk their solutions. And the outcome from these testing or projects, they can showcase that to other transmission owners or even New York's ISO. So here is a couple of example projects that we have completed with our stakeholders. So one example that I can discuss is about the second last one, impact of modular power flow control on line protection. In this case, what we did was use an actual line protection relay interfaced with our digital real-time simulation platform. And we run a scripted contingency of more than 10,000 events to test whether the relay responded accurately to each and every event. Another project that I can talk about is the one at the bottom, that is behind the meter, DR-provided grid services. In this case, we ran a tightly coupled transmission and distribution co-simulation running in real time, which consisted of 5,000 bus New York State model of the transmission grid, 10,000 node distribution model interspersed with thousands of DARs. And what we were trying to assess was, in the case of, let's say there's a big disturbance in the transmission grid, how does the DARs in the distribution grid respond to that event by providing frequency and voltage support? In the next set of projects, if you look at the top, tracking real-time anomalies in power systems. So in this case, we worked with our cyber group to test intrusion detection systems by emulating communication network signals that are typically prevalent in substations. And once we verified and validated it, now this solution is completely deployed across all of the NYPA stations. So what I want to summarize over here is we have prepared a service catalog that showcases all our capabilities and offerings if you belong to an ISO or a utility, R&D, or any other academia. And we have a service catalog that you can either scan it through the QR code, or I also have it available, the physical copies of it in the booth. And the easiest way to reach us, if you need to discuss further about any opportunities, is to send us an email on agile@nypa.gov. I think that's it. Thank you.
Thank you. And I'm going to encourage you all to go visit Rahul at his table out in the lunch area. And with that, we're going to take a lunch break, which is a little longer than we're going to do tomorrow. So come back here at 1:45, but we'll certainly let you know when we're convening again. So enjoy lunch, and thank you.